My name is Russ Cam, and I'm an engineer at Elastic, and I work on the language clients team. So I've been at Elastic for around 4 years now, and my background is in software engineering, primarily with the Microsoft technologies. And I have interests in cloud computing, distributed systems, software design, principles, patterns, and practices. And you can find me on Twitter at @4loop. So today I'm going to talk about exploring Stack Overflow data with the Elastic Stack. So just a brief look at what we're going to kind of discuss in this session. It's going to be somewhat of a whirlwind tour of a talk. We'll be skimming the surface on many topics, but my primary aim is to provide you with an end-to-end introduction on how to start using the Elastic Stack to explore a data set. So depending on how we're doing for time, we may have the opportunity to go into some areas in more detail. So the agenda today is going to be a brief introduction to the Elastic Stack to set the context for the technologies we're going to be looking at, followed by a look at the Stack Overflow data to give us an idea of what we're dealing with and what insights we might want to get out. Then we'll talk about ingesting that data into Elasticsearch. We'll look at some search and aggregations. And finally, we'll build some visualizations and dashboards to aid our exploration and analysis. So I suspect many of you have heard about Elasticsearch or the Elk Stack before. The Elk Stack is an acronym that grew out of the community many years ago, and it's kind of short for Elasticsearch, Logstash, and Cabana. But as the stack is kind of scaled over time to incorporate new products like Beats and APM, however, the Elk acronym hasn't really scaled in the same kind of way. So now that we add APM and Beats into the fold, what do we end up calling the stack? Do we call it the Elkba stack? How about the Caleb stack? Or perhaps even the Bleak stack? So we actually refer to it as the Elastic Stack. And that comprises the following things. So at the core is Elasticsearch. And Elasticsearch is a search analytics engine. You can run it as a single node, you can run it as multiple nodes in a cluster, i.e. it is a distributed system for storing and searching and analyzing data. So you interact with it using JSON over REST APIs, although it is possible to interact with it with SQL over JDBC or ODBC connections too. You index data into Elasticsearch in the form of JSON documents, and a collection of documents go together into an index in Elasticsearch. It supports complex full text search, geospatial search, and aggregations, and you can combine these in sort of various different ways for various different use cases, for example, for monitoring, for full text search, for geospatial search, etc. Importantly, it's fast and scalable, and the responses to it are very near real time. Then we have Cabana. So Cabana is the window into the Elastic Stack. It's the web application that you can use to manage and monitor the stack, and you can build dashboards and visualizations within Cabana to display and present the data that you have in Elasticsearch. Then on the ingestion side, we have a bunch of different tools available for you to use. So starting on the left-hand side here, we have Beats. So Beats are a suite of different lightweight data shippers that allow you to send various different types of data to Elasticsearch or to Logstash. So some examples of that might include FileBeat, so where you can ship log files or any files with a structured format. PacketBeat, for example, for shipping network data, which supports multiple different protocols for various different databases like Postgres or other protocols like HTTP or DNS. AuditBeat is another example that you can use to monitor user activity and processes happening on servers and machines within your environment. Then in the middle, we have Logstash, and Logstash is a powerful and flexible ETL pipelining tool. You can take data from a multitude of different sources, you can transform it and enrich it in many different ways, and you can output that to somewhere else, including to Elasticsearch. So Logstash, you typically kind of run somewhere centralized, and then you would ship data to it from various different locations within your network or your environment or organization. and then you would aggregate that data, filter it, enrich it in that one place, and send it on to Elasticsearch. Then on the right-hand side, we have clients. So Elasticsearch being JSON, REST, HTTP API, we have clients here available for all the various different languages, popular languages, programming languages that people use. And these clients are configured to take advantage of various different things like connection pooling, failovers and retries, round robin requests over nodes within the cluster. So you can write bespoke integrations with the clients there. So you can run it on the cloud. You can run the Elastic Stack on the cloud, or you can spin it up yourself and self-manage it. And it fits a variety of different use cases. So some examples here. So on the application site search side of things, Wikipedia, Stack Overflow use Elasticsearch to power the search on the websites. Uber uses Elasticsearch to match drivers to riders. Tinder uses it for profile matching. Netflix uses it to monitor operations and outbound messaging. I think that one of the true sort of powers of the stack is the flexibility and the capabilities that it has to fit a variety of different use cases. So today we're going to be talking about Stack Overflow data. So let's begin our journey by exploring what that actually entails. So before we kind of get started on that, I suspect everyone here is probably familiar with Stack Overflow already. But for those of us that aren't, Stack Overflow is a question and answer website for programmers. It has become one of the most popular and trafficked websites on the internet. And it has kind of become the de facto resource for many programmers and developers for their day-to-day jobs and hobbies. It has around 17.7 million questions, or it did when I looked at the data set a couple of months back, and the data set that I grabbed for this presentation now, with around 27 million answers to those questions. And the company behind Stack Overflow, Stack Exchange, makes all of this data available from the site under a Creative Commons license. So they make this data available in a collection of zipped XML files, where each item is an XML element in a file with attributes and values for the properties of the item. So there are also around 10.9 million users of the site, many of them being regulars. But how does Stack Overflow get users engaged and keep them engaged? Well, users are incentivized to participate by gaining reputation points from other community members for good questions and answers through a voting system. And with reputation gamification in place, as well as the general nature of some people wanting to help others in the community, this has seen the rise of certain individuals who appear to be answering all questions at all times with an accuracy and detail unsurpassed by any current generation chatbot. So John Skeet, an engineer at Google in the UK, has become the highest reputation user on Stack Overflow, leading many to dub him the Chuck Norris of programming, and leading to a humorous discussion topic on the Meta Stack Exchange website about John Skeet facts. So these gems include things like John Skeet can determine the next random number in a sequence. And when John Skeet throws an exception, nothing can catch it. So it's very likely that John Skeet has answered a programming question that you might have. And for that, there is askjohnskeet.com, a website powered by Elasticsearch, written by a community member that can search the Stack Overflow answers of the great one himself. I just want to point out, we are in no way affiliated with this website. It was put together by a community member just to learn how to use the stack. So on a more serious note, we're going to index all of the Stack Overflow data into Elasticsearch, and then it's going to allow us to explore that data, building up a dashboard of visualizations in Cabana, similar to what you can see here. So to get there, we're going to have to go through a bunch of different steps. So the first thing we need to do is we need to take a look at the data itself. We need to see what fields are available and how they're formatted in those XML files. And we need to start to formulate an idea about how we're going to model that data in order to serve our search needs, our search and aggregation needs. So then once we've done that, we can then decide how we're going to get the data into Elasticsearch. So we could use Logstash, we could use Beats, we could use one of the clients, or we could even just use the HTTP REST API directly if we wanted to, although that might take some time to do so. Finally, once all the data is indexed into Elasticsearch, we'll reach the point then where we can start to explore the data set and gain some insights. So now let's start to have a look at exactly what is contained within those XML files. So if we look at the posts XML file here, it's a humongous file at 81 gigabytes. We can start to kind of figure out how the data is laid out in here and what we're dealing with. And I think it's important to stress that it's a good idea to go through this process of analyzing the source data, because it's probably going to influence how we decide to index it at a later point. So if we look at this, for example, we can see that here it contains questions here. So questions are denoted with this post type ID of 1. And then we have answers here, which have this post type ID of 2. So all of the properties of a post are defined as XML attributes, as you can see here. It's a bit of a mess, but you can see they're all defined as XML attributes. And that means inherently that all of the data here is actually modeled as strings, even though we know that technically this is a numeric type here. This is a string, but it represents an ISO 8601 date. Other things of interest here is that the body here contains a string, but it also contains encoded HTML tags here. So we have a starting P tag here, we have a closing P tag down here. So when we index this data into Elasticsearch, what we'll probably want to do is to remove those HTML tags when analyzing it and indexing it. But perhaps when we want to show it back to the user, maybe we want to show it back verbatim, including those HTML tags. So if we then look at the user's XML file, it's a similar kind of story to what we kind of saw there in the post XML file. Each row here is a user. Oops, sorry, beg your pardon. Just jumped forward a bit there. So yes, each row here is a user with a display name and a location, and an about me here that also contains HTML tags. And then if we also look at badges, so these are the badges that users gain when they gain reputation on Stack Overflow, when they answer a certain number of questions related to a particular topic. We can see here that there's one row per user ID per badge. And similar story to what we saw beforehand. We have attributes here, false, 3, date attributes here for the badges. So we've kind of had a look at the raw data that we're dealing with. What questions do we want to ask of the data now that we have it? So this doesn't really need to be an exhaustive exercise, but I think it's important to think about these questions up front, because it is going to help us to determine how we do want to model it. So Elasticsearch itself has been described as schemaless before, but I actually think it's worth thinking about it slightly differently. So when you index data into Elasticsearch, you don't have to define a schema for that data ahead of time within the index. And what Elasticsearch will do is it will infer a mapping or a schema for those documents based on the first one that it sees indexed into an index. But when you're performing a search use case, you often actually want to be explicit about defining that schema or mapping ahead of time when the index is actually created, because then that allows you to control exactly how those fields are mapped. And make them fit for purpose, because you might want to do things such as analyze fields in a particular way. You might want to have certain fields indexed in more than one different way to serve different purposes. So we saw that on the user's XML file that we have this location field. So that location field, so if we just jump back a second, this location field here is actually represented as a string, and we know there that that is very likely a location somewhere on Earth, hopefully. And it would be nice to index that as a set of latitude and longitude coordinates into Elasticsearch. Unfortunately, we aren't going to be able to do that for this presentation today, because it does require us to use some tools to be able to perform that reverse geocoding. There are several open source projects that we could use to do that, but for the volume of data that we're talking about for tonight, I haven't had time to prepare that. But if that is something of interest to you, where you do have a collection of user location strings, and you would like to get the lat longs for those there, and those strings are reasonably arbitrary in nature. There are libraries like libpostal and Peleus that would allow you to take that and get some latitude and longitude out of there. That's kind of more than we can cover for today, but those are projects for interest if you're interested in that kind of thing. So we've gone through the Stack Overflow schema, and we've gone through the files, and we've had a look at the data, and we've come up with this mapping of how those map to these particular entities. So we've got 4 entities here. We've got questions, we've got answers, users, and their badges. At this point, it's useful to kind of go back to the questions that we'd like to answer. So one of those is being able to look at questions and answers by tags. So tags are the particular topics that a question relates to. And we can see here that tags is represented only on the questions, but we would like to ideally be able to also analyze and aggregate on answers for particular tags too. So what we might want to do while we're indexing this data is also transpose those tags from each question onto the respective answers for that question. So if we were thinking about how we might model those entities and the relationships between them using a normalized relational model, then we would probably come up with something like this. So normalization helps us in terms of limiting duplication and enforcing referential integrity. And you might have been told or read about persisting data in third normal form beforehand, because it's very typical to do this in relational databases. So with third normal form, the data should be dependent on the key, the whole key, and nothing but the key, so help me God. But normalization isn't really a panacea for modeling all kinds of data problems, particularly when you start dealing with really, really large amounts of data that may be spread across a distributed system, such as Elasticsearch. So one of the things in particular are joins, which can dramatically affect the performance in such systems, particularly when the data is not co-located across that distributed system, but it's spread across multiple different locations. So if we were taking this model as an example here, if we wanted to return data about questions, answers, users, and badges in one result set, it would actually require us to make 4 joins across those 4 different sets of entities to be able to do that. And you know, that can very much hurt things, hurt performance at scale. So that's typically why people often tend to denormalize data when they're dealing with large amounts of data. And it kind of leads to the normalize till it hurts, denormalize until it works adage. So get comfortable with a little bit of denormalization for tonight, or for today, as that's where we're going to be modeling Stack Overflow data in Elasticsearch. So as I briefly mentioned before, individual entities are represented as documents in Elasticsearch, and a collection of documents are indexed into an index. So for the Stack Overflow data, I've decided here to model that as 2 indices, a posts index and a users index. So in the posts index, that's going to contain question and answer documents, and the users index is going to contain users and their collection of badges on each user document. So I've configured the questions to have a parent-child relationship with answers, which you can do within one index. You can set up parent-child relationships, and that is a query on answers given questions that match some criteria, and it would allow us to do the inverse as well, which it would allow us to query on questions given answers matching particular criteria. So one of the downsides, so parent-child relationships are flexible in that manner, but one of the downsides potentially is that answers to a question need to be stored in the same shard within an index. So I haven't really mentioned this previously, but an Elasticsearch index is split up into shards, and those shards then live on across the nodes of an Elasticsearch cluster. So if your child answers need to live on the same node as the parent question, it can lead to hotspots within particular areas within the cluster, because some have many answers and questions may have no answers. So you can end up with, you can possibly end up with a slightly uneven spread of questions and answers across the cluster if you go for a parent-child relationship, as I've done here. The other thing here to note is that because I am indexing questions and answers into the same index, the relevancy scores of questions and answers affect the relevancy score calculations for both of them, even if the query may only be looking at, for example, answer documents, or it may only be looking at question documents. The relevancy score of all documents within that index are affected. So, so I could have modeled these slightly differently. I could have modeled these as separate indices. So I could have put questions in one index. I could have put answers in a different index, and I could still have queried across both of them within Elasticsearch, because you can still query across multiple indices. I could also have here, I could have indexed them as time-based indices too. So every question and answer has a created date on it. So what I could have done is use that created date to determine which index to index a particular question or answer into. So I could have, for example, have had time-based indices based on month of the year, and then indexed those documents that relate to that were created within that particular month and year into that index. So we have an idea here for how we're going to index it. I'm just keeping it relatively simple and just going for two indices. So with the index and document plan in place, the next thing to think about here really is about creating those indices and creating the mappings or schema for the documents that are going to be indexed into them. So as I mentioned just a second ago, an Elasticsearch index is split up into a number of shards. So n number of shards, where you get to define what n is when you create the index. And each shard can live on a different node within a cluster. So then each shard can be replicated to other nodes, such that in the event that a node were to go offline, there would still be a complete set of data and the cluster would remain operational. So we won't really worry too much about that for this talk, because that's probably a whole talk in and of itself. But suffice to say, it's something to think about when we're at least creating the index here. How many shards do we want to create this index for? And some of the reasons why you might decide on the number of shards is, for example, how many nodes you have in your cluster. So in this particular talk, I have a 3-node cluster that I'm going to be running with. So I believe I've indexed this, created these indices with 3 shards, so I can split the data across those 3 nodes within the cluster. So we had a look at the XML files, we had a look at the data types that we were dealing with there. So we need to think about how those data types are going to map to the types that we're going to use in Elasticsearch. So most of these are fairly straightforward. So numeric fields, we can index them as integers, as longs, as doubles, as floats. There are a few other numeric types there for more specialized use cases. Date strings that look as though they're ISO 8601 dates, we will index those as dates. There's a few interesting ones here there that I want to call out. In particular, strings. We might decide to index them as text data types in Elasticsearch, or we might decide to index them as keywords. Now, the difference between those two is that keywords will index that piece of text exactly as is. So if you wanted to search for a piece of text exactly as it is represented in the source data, then you might want to index it as a keyword field. If, however, you want that data, that string, to be analyzed when you index it, such that you can then perform full text search on it at a later point, then you might decide to index that string field as a text data type. One of the advantages you can do here is that if you need to index a string field in a multitude of different ways to serve various different needs, various different search needs, you can actually index a string field or any field in multiple different ways using something called multi-fields or fields when you index it. So I don't have an example there on that particular image, but we could have a look at that when I jump into some examples in a second. The other thing really that's worth pointing out here is that the parent-child relationship that we're going to define between questions and answers, there is a specialized field for that called the join field. And essentially that allows us to identify for a particular document, whether it is a parent, i.e. whether it's a question, or whether it's a child, i.e. it's an answer, and what the parent document for that answer document is. So that's what the join field allows us to do. So yeah, I will touch briefly on analysis. So in that questions and answers data, we saw that the body of a question has HTML tags in there. When we index that into Elasticsearch, if we index it as a text data type, we can define something called analysis for that text data type. And that basically allows us to send that string through a series of stages which allow us to extract the most meaningful data, i.e. the tokens, from that string of characters, and index that into Elasticsearch in order to service our full text search needs. So that analysis might do things such as strip the HTML tags as it's reading through the text. It might decide to lowercase all of the string coming through, and it might be removing stop words for a specific language. So Stack Overflow, the main website is in English. So the stop words here might be the English stop words like the, a, and, etc. So when we looked at the data, that post's XML file was around 81 gigabytes, and we had a 3 and a bit gigabyte user file, and we had a 3 and a bit gigabyte badges file. So how are we going to get around 90 gigabytes of data into Elasticsearch? Well, the naive way is we might just decide to open the file and read the file and index it line by line into Elasticsearch. But the problem with that is that ain't nobody got memory for that. Nobody has 90 gig of RAM sitting around, unless you're extremely lucky, to be able to open a single file into memory and then index from there. So what we're going to have to do instead is stream the questions and answers from that post's XML file and read them, buffering only a small amount at any one time in memory. Now, I could have used Logstash or Filebeat, one of the beats for this particular purpose, but the engineer in me took over and I couldn't help writing a small program specifically for this purpose. So what you see here is just a small amount of C# code that's written using the official .NET client that we have. Don't be afraid, I will talk through it. If you're not familiar with .NET, that's fine. But essentially what we're going to do is open up a file here. So open up a stream to a file. We're going to create something that's going to allow us to read the XML from that stream. And then essentially we are just going to keep enumerating over that file. So we're only reading a small amount into a buffer each time. We're going to look at that post type ID attribute that we had. And if it's 1, we know we're dealing with a question and we can construct a question type. If it's a 2, we can construct an answer type. And we're going to return this as an IEnumerable of post. So the most crucial part here is that we're actually just going to return out these questions and answers from this particular method. And what that allows us to do is that it returns that individual question or answer back to the caller, and it suspends the streaming from that XML file at that point. Then when the caller asks again for the next question or answer, the code continues from that suspended point. So taking this as an example, we read through the first time, we return a question or answer, this call is suspended here at this point. Then when the caller of this method here asks again for the next question or answer, we're going to go back around this loop here and keep going until we've finished all of the rows within that XML file. So this allows us to stream that 81 gigabyte file with an extremely small memory footprint. So on the other side of reading the data out of the file, we need some way to actually stream that into Elasticsearch. And this is where the .NET client comes in. So here we're using the .NET client and we're using the bulk API. And within the .NET client, there is a specific helper that can help with bulk indexing a stream of documents, which is this bulk all method here. And what we can do here then is we can define how many bulk requests are going to be concurrently sent to Elasticsearch in order to index all of this data. So this small piece of code here is going to send multiple bulk requests to Elasticsearch concurrently, with each request containing 1,000 documents. So it's going to continue to do that until all of the questions and the answers are indexed. So on a reasonably spec'd laptop, if you like to try this at home, and I have a link to this code at the very end of the presentation, if you'd like to try it at home, it'll take you around 90 minutes to index that 81 gigabyte file on a reasonably spec laptop, which works out at around 515,000 documents indexed per minute, which is pretty reasonable. And because there's a fair amount of analysis that happens during that indexing. So that's a pretty good rate. So once that indexing process is finished, so we've set up our streaming to read, we've set up our streaming to write to Elasticsearch. Remember that we said that one of the ways that we might want to be able to explore this data was to look at questions and answers by tags over time, and that tags were only present on the questions within the source data. So what we can do is, once all the data has been indexed, is we can go and update the answer documents to add a tags field containing the tags of the parent question. And so this is what this API call here is going to do. Again, using the .NET client, it's going to allow us to run an arbitrary script here. So this here is a script written in Painless, which is the dynamic scripting language that you can use with Elasticsearch. And it's basically going to look at answers that match for this particular question ID. If an answer already has tags, then just ignore it. But if it doesn't have any tags on the document, then index it, update it to include these tags on there. And we can run that across all of the answer documents. So that's a kind of brief rundown of looking at the data and indexing it into Elasticsearch. And what I want to do now is to take the opportunity to actually look at some of that data within a live cluster. So I'm just going to stop sharing now at this point. And I'm just going to switch over to another monitor. Okay. And right, okay, so what I have here is I've taken all of that Elasticsearch data, I've indexed it into a cluster that I've spun up on our SaaS offering on Elastic Cloud. So this is running here in Sydney, I'm up in Brisbane, so hopefully the latency won't be too bad. So the first thing that we do when we first open up Cabana is we're presented with this screen. So we've already indexed the data into Elasticsearch. And if we want to be able to search over it, we can go to the dev tools here. And this allows us to execute arbitrary requests against Elasticsearch using the REST API. So we could, for example, do a GET request to the posts index and to the search API endpoint. And if we execute that here with this arrow, or we can just press Control Enter, we can see the results here returned. So the results are returned within JSON. The documents that we're interested here are within this hits array on the response. And you can see here that we have the bodies here that include the HTML tags like P and pre and code. And we've returned back the first 10 matching documents. So we can do an easy search. Let's say if we search for questions and answers containing Elasticsearch, so we can execute that one here, and we get back results. So there are at least 10,000 hits that match here, and we've seen the first 10 documents returned. So they're returned in score descending order. So the most relevant document is returned first, and we can see here that this one does contain Elasticsearch in the title, it contains it in the body here, it also contains it as a tag, and so on and so forth. We can get a little bit more interesting here with searches. So we can say, well, show me answers that are related to Elasticsearch only. So we can perform a more complex query here, which is a Boolean query, which is a combination of two different query elements. So as before, we're looking for Elasticsearch, but we're going to filter it to only look at answer documents within our posts index. So if we run that again, we will see that the results that we get back are only going to be answer documents, and again, containing Elasticsearch. So that's kind of a brief way that we can ad hoc search that data. We can also do other various operations inside of here. So we can look at and see what indices are available within Elasticsearch. So there's a bunch of internal indices there, but we have our posts index and we have our users index, and those are the ones we're interested in here. That's all well and good for doing ad hoc queries. What we probably want to do is maybe just kind of look at those from a higher level. So this is where the Discover tab comes in. So at the top here, we have the Discover tab. So we're looking here across 44.8 million documents. So that is all the questions and the answers together in the posts index here that we're looking at. And so we can see the individual documents are here, and we can expand each one. We can look at the fields in a table, and we can look at that document as a JSON blob instead. We may only be interested in looking at particular fields though, in which case we can just filter these just to say look at the title. So we'll have the time here and the title. So let's get rid of that. So title, and then we might just want to look at the comment count. So we can just focus in only on the particular fields that we're kind of interested here. And in fact, we can just save this as a Discover tab if we want to. So we can go up here and save that search. So I have one here saved from before, which is looking at questions and answers. And it's only looking at the various fields that I want to kind of look at. And this is great for being able to eyeball particular data. So we can see whether it's a question or an answer. We can see the title of it. We can see the tags that are related to it, the score of it, the answer, and we can sort by any of these columns here too. One thing that is of interest here is that within Elasticsearch we can define scripted fields. So we can define dynamic fields for each of these documents to be displayed here in Cabana when they're returned. So what I've done is I've created a scripted field here that links back to the original question or answer on Stack Overflow. So you can see I'm not cheating here. So if we take this one, for example, and look at this answer, it opens up here and it links to this particular Stack Overflow answer here. And if we just expand this one out and look at the body of it, we would be able to see that the body here matches the body that we saw there on the Elasticsearch site. So we can, similar to what we were doing within console, is we can search here for Elasticsearch, for example, and it will flag those that are tagged as Elasticsearch. We might be able to do Elasticsearch. So let's just change to KQL. Actually, no, let's just keep it on here. So we might want to look at those that are tagged Elasticsearch. So tags Elasticsearch. So those that mention Elasticsearch and contain the tag Elasticsearch. So yeah, we can see those highlighted here. We can also, if we want to, we can just, if jumping back to Cabana console here, we can just paste a query from here directly into the Discover tab at the top here. So make sure you've got Lucene as the query language configured, and we can paste that directly into there and use that to search only on answers that contain Elasticsearch. That's kind of one way where we can kind of start to explore documents and look at them within a table, and we can look at surrounding documents for a particular document, surrounding here being based around the time at which that answer was constructed. That's kind of that's super useful for being able to look at it in that kind of way. Wouldn't it be great though if we can start to be able to visualize this data? So the next thing we probably want to do is go and look at creating some visualizations on top of that data. So if we go and create a new visualization, and let's just say we want to go and create a metric, for example, looking at the post index. So it gives us a count here straight away, and we can go and save this as a visualization. So Stack Overflow Q&A count. That's one visualization that we've saved. So we can jump back to visualize, and we can go create another visualization. So let's just say we want to look at, yeah, let's look at an area chart again over the posts index. So we want to bucket this data by date. So we want to look at creation date only. Say, let's see what that looks like. So we can see a count here. We may want to make this into a bar chart. Okay, so we've got it as a bar chart. We may want to split these buckets potentially. So add sub buckets, and we might want to split the series here. And let's say we want to split them by tags. So let's say we want to look at the top five tags within each date bucket. So if we run that now, again, we're looking at the counts of those tags. So it's just thinking, there's a fair amount of data to crunch there. So yeah, so we can see the top 5 tags per bucket here over time for that entire date range. And if we want to, we can look at, say, just the last section here, which is going to filter to that particular date range. And then again, we can save that off as another visualization there. So we could say tags over time. Tags over time. So we've got a couple of visualizations. The next thing we kind of want to do really is look at all of those within a dashboard. So a dashboard is going to allow us to group all of the visualizations that we've made and put them all together into one single place. So I've put together a few visualizations previously, and I've put them together here on this dashboard. And this starts to give us an overview of exactly what we're looking at in the back of data. Got 7.7 questions, 27.1 million answers. The tags here, JavaScript, Java, CHB, Fern. There's a tag cloud here where the size of the word is a more prominent tag within the data. Again, we have questions over time, answers over time, top questions, and some metrics like standard deviations and percentiles for each one of those tags. So within here, we can start looking at, for example, we can look at tags and equal some value. So I am a C# engineer, so I work often with C#. So let's look at C# and tags, let's say .NET, yeah, .NET Core perhaps, and let's see what we're looking at there. So you can see when I entered that search, all of these panels refreshed to reflect the data that I'm searching for, and I could say and type. I'm only interested in the KQ query language within the search bar is filtering down to particular values that are within that type field. So yeah, we can look at just answers in particular, and again we can see those answers over time. So yeah, we can just filter down to just look at this particular date range here, and we're looking at 770 answers over that time. And again, we can click a particular thing here, and we can add it as a filter up here, and we can further filter data down this way. So let's go on a little bit of a journey. So starting back here at the Discover tab and looking at the users index. Let's have a look. So let's have a look and see if we can find John Skeet in here. So we're looking at this date range, didn't find John Skeet within that date range. So we just need to change this to look at the entire date range. So everything from 2008 when Elasticsearch, when Stack Overflow started. So we can see John Skeet here at the top. So what I've done here is created some scripted fields so that we can look at John's questions. So we can launch here and look at John's questions in the Discover tab. And similarly, we can look at John's answers too. But why not? Let's go and have a look at John's questions and answers on the dashboard that we set up. So if we click this link here, that's going to take us to the dashboard, and it's filtering here by the user ID for John, which is 22656. So we can see some fairly interesting things about John's profile. So John is asked 50 questions, but he is a prolific answerer on Stack Overflow, and that's actually where he's gained the most reputation. We can see here that John mainly answers C# and Java questions, and we can see that gradually over time, you know, John was very, very prolific, and over time, you know, he's steadily sort of answered less questions, but is still the #1 answerer on Stack Overflow. What's kind of interesting here is that we see that John's extremely prolific in C# and Java. So if we want to have a look and just kind of understand, well, who are the top kind of answerers for C# and Java across all of Stack Overflow, we can jump back into the visualizations here. And if we jump back to look at the top tag answerers and look at those as a heat map, what I've done here is simply plotted the top tags in top 5 tags in Stack Overflow in descending order, and then for each of these tags, I've just listed out the top 5 answerers. So that's by score descending. Yeah, so yeah, sum of score descending. So the numbers you see here on the left-hand side are the user IDs for users on Stack Overflow, and down the bottom here are the tags. What's kind of interesting here, looking at the top 5 tags, is that this user ID here is the only user who is in the top 5 answerers across 2 different tags. And that happens to be our good friend John here. He's extremely prolific in Java. He's the highest C# question answerer, and the 3rd highest Java question answerer, which I thought was kind of interesting. If we jump back to our dashboard, again, we're still on John. Does John ever answer any questions about Elasticsearch? We can go and find out, and no, he doesn't. He doesn't seem to have answered a single question about Elasticsearch. Well, let's try that with him. Nope, it's not answered any questions about Elasticsearch. So that's kind of a very brief overview of Discover, how to build visualizations and how to put them together in a dashboard. One of the other things that we might want to do here too is to look at questions and answers over time and understand if there are any particular anomalies or unusual events within that data over time. And that's where machine learning can help us. So one of the things that we can do here within the machine learning tab is we can create a job, and we can look at particular metrics over time at particular indices and understand if there are any anomalies that have happened. So we can create a simple machine learning job for this. So looking at the posts index, just looking at a single metric. Yes, let's use the full post data. Let's just say we want to look at the count of questions and answers over time, and say the bucket span we want to look at is, I don't know, let's say 24 hours. So we'll look at buckets over per day. So we'll bucket that data into daily buckets, and then understand, see if there's any anomalies within it. And we'll just give that a name, Q&A count. And then we will just, we will use a dedicated index for that. And then we will just kick off that machine learning job. So I ran one earlier, just looking at the question and answer counts over time. So I'm just going to jump back to machine learning, back to the jobs list here. And I had this question and answers count that I ran over that data earlier. So we can open up what that job running over the data is going to give us. So if we look at the entire data set here, what we can see here is that this is the count over time, and the circles and crosses that you see here are particular anomalies that the unsupervised machine learning job has picked up running over that data. So anything flagged as a red anomaly has a high anomaly score, anything with an orange slightly lower, yellow lower again. The blue bounds that you see here is the model as it's been learning the data. One of the things I wanted to point out here is that I just ran this without really, across all that data, without any preconceptions about exactly what I was looking for. But what was interesting is that this ML job did pull out some particular salient times where it detected a high anomaly, and it gives you some understanding of what that anomaly is. So, for example, on January 2010, 2nd of January 2010 here, severity of 98. Typical value it sees is 23.5, but it saw 40. It's twice as high as it normally sees. One of the interesting things is that 2nd of January 2010, 3rd of January 2010 was when Stack Overflow launched its careers website. So there was more traffic. There was more traffic on the site at that point in time, which the ML job has picked up. Some other interesting ones here that I saw is this 15th of September 2008. Traffic was 7 times higher on 15th of September 2008. And the reason why is that was actually when Stack Overflow came out of beta and went live on the internet. So it's kind of unsurprising, really, that we see such a large kick up in questions and answers on that particular day. And just to give you a flavor of another one here, this 30th of October 2013, where the count of questions and answers was 12 times lower. As you can imagine, Stack Overflow was actually down on that day, and it was down for a fair amount of the day, which is why the traffic was quite a large amount lower. So we've been able to glean some insights there from the data, historical insights, that is, from the data, without really having any preconceived ideas about exactly what it was that we're looking for. We just set up an ML job, ran it across the data, and it gave us some anomalies out there for us to go and have a look at. One of the other things that I'd like to just show off briefly here is another way that we can kind of go and look and explore this data. So I've shown how we can visualize it. I've shown how we can put it into dashboards. I've shown how we can run anomaly detection over it. One other thing that we might want to do is to understand if there are any relationships amongst the questions that people ask and the answers that people provide. You know, if people ask questions about C#, you know, maybe what are the other likely tags that they are going to put on that question based on the corpus of documents that we can see here. So we're looking at the posts index. And let's say, again, we're looking at the tags field. If we simply do a search here for C#, what it's going to do is bring us back questions tagged with C#. Typically, or we usually see them tagged with .NET, which is unsurprising, but some other significant tags for C# are compiler version, .NET Framework version, C#6, the name of keyword, C++, CLI. Let's have a look at F#, which is another programming language on the .NET Framework. So these are the tags most associated with F#. So things like unit type, type providers, fake, which is a build automation in F#, and scripting in F#. What's interesting actually is that this island of related tags or significant tags to F# is kind of separate to the island of tags that are significant to C#. But what we can do here is select the C# tag, select the F# tag, and see if there are any related links, any related tags between those two. So we can expand here, and we can see that, oh wow, okay, there's one tag here, Catalan tag, which is heavily significant with F#, which we can see here. So F# has this Venn diagram here. The F# tag is appears 37,000 times, and the Catalan one appears 321 times. But there's also some overlap here with C#, and we can keep expanding out and seeing what other tags are related to the two. So NML is another .NET language. It's a community .NET language, and garbage collection allow very large objects is another tag significantly related to F# and C#. I was a bit confused when I looked at this, first of all, because Catalan, I was thinking, are there many developers in Catalonia in Spain that are interested in F# and C#? But it is actually, for the mathematicians among us, it is related to Catalan numbers that tag relates to, which we can go and see if we jump back to the Discover tab, and we were to go and look at tags that are C# and tags that are Catalan. And if we just take this back down to, looking at all of the data, and helps if we're looking at the post index. Sorry, 1 second. Let's try that again. Okay, so let me just use my questions and answers tab that I have. Saved query. Okay, so these things with C#, and this one should also have Catalan there as well. Nope, never mind. But I was going to say we can go and link back to Stack Overflow and go and look at one of those questions or answers that is tagged with Catalan, and then we can go and see that it is about combinatorial numbers, Catalan numbers. So just jumping back now back to slides very quickly. And perform full text and structured search using those scripted fields such as questions, answers, and dashboard here for dynamic calculations and creating links within the Discover tab, and being able to use Discover to explore surrounding documents. Then we looked at constructing a single visualization and then bringing all of those visualizations together into a dashboard, which we can then use to search across to explore trends and patterns. Then we looked at some machine learning jobs, and we saw that just simply performing a machine learning job across all questions and answers managed to pick up some anomalies there, and the dates for those anomalies correlate with particular events that happened on the Stack Overflow site at that time. And then finally, we did look at graphing the relationships between tags. So these are inferred relationships between fields within the documents to understand those that are significant relationships, or those that are simply a large, there's a large count overlap between those particular fields within those documents. And we can use those things to power recommendations. So for example, based on a user putting in a question about C# and tagging it as C#, we could use all of the questions and answers that we already have to recommend to them which other tags they might want to tag their question with. And we can also use graphing here to perform ad hoc threat hunting. So if we're indexing security data, for example, which we're not doing here, but so we are indexing like firewall logs or other kinds of logs, we can use the graph here to then go and explore that data to understand and write out different threats that may be appearing within our network. So the key takeaways for today, and I'll get around to some questions afterwards, is essentially to analyze your source data, to go and have a look at the source data to understand what you're dealing with. Then to look at modeling it in order to answer the questions that you are looking at. So you might make decisions around how you decide to split up into indices, how many shards are in each one of those indexes, the mappings for the particular documents that you're going to index into that index. Then on the ingestion side, whether you're going to look at using Logstash or one of the beats, or whether you're going to write something more bespoke using one of the clients like we did here. There's a link there to the GitHub repository that contains that Stack Overflow indexer that I showed you. So if you want to play with that, you can do. And then finally, exploration. So we looked at just exploring the individual documents, performing some ad hoc queries, exploring them in the Discover tab with visualizations and dashboards, and then also running some machine learning and graphing some relationships on top of those. So that is all I wanted to cover today. I will have a look and see, have a look at the questions now and see what people are asking. So let me just stop sharing. For some reason, my camera decided to stop working. Ah. Okay, there we go. Yeah, so let me just have a look through some of the questions that have been asked while I've been talking away. So yes, so typically, so Chandan Kumar asks, typically as a user, I visit Stack Overflow through Google search. How is Stack Overflow's search response time and ranking wise as compared to Google? That's a very good question. I think it's probably useful to ask to answer that question in a slightly different way. I think one of the things that Google is obviously very, very, very good at is indexing the web and indexing pages on the web. And Stack Overflow probably goes to great lengths in order to ensure that their questions and answers are SEO friendly in order to appear higher up in the rankings within Google for particular questions or answers. But they kind of, they probably are trying to serve slightly different needs in the sense that for a public site like Stack Overflow, where they understand, they have some structure behind the questions and answers data within their system. They understand, you know, that a particular question has tags associated with it. They understand, you know, there's a title, there's a body. They understand whether they might be looking at things like whether a question has been favorited many times or whether it has been upvoted many times. Google, on the other hand, doesn't have that domain data. What Google has instead is essentially what they see on the web page, which is going to be basically a collection of HTML and JavaScript. So Google has to perform their searching and their indexing of that data in a slightly different way. And what that means actually is that Stack Overflow potentially has some advantages in terms of how they present results to a particular user. So they, it's very easy, oh sorry, I should say it's easier for them to do that than it is, say, for Google. Because Google needs to understand the semantics of what is presented on that HTML page, whereas Stack Overflow already has that data in their model. So they could say, for example, present you questions that are voted higher by the community for a given thing that you're searching for over those that have been downvoted or voted much lower. They might also more easily be able to present you those questions that have an accepted answer to them already, or potentially a question that has answers to it, and they might be able to surface that to you as a response and favor that over a question that has no answers to it. So that's kind of one of the advantages that Stack Overflow has. Ranking wise and response time, I mean, Elasticsearch, you can very much use Elasticsearch, you know, for very single-digit millisecond responses if you have a sufficiently large index, sufficiently large cluster. So it's often common for people to be able to, serve data in those kind of times. Ranking wise is probably a whole, that's probably a whole conversation and Meetup talk in and of itself. Suffice to say though that Google pulls in signals from many, many other different data sources purely than just the text that they scrape from the web in order to service you up results when you search on Google. Yeah, it's much more complex than simply looking at the source data. So one of the questions was, have you open sourced the scripts which crawls through Stack Overflow? Yes, I have, and we can present the the links to that and the slides to everyone afterwards, so they can go and have a play with that. That particular script, that small application, will run cross-platform. So whether you're running on macOS, Linux, or Windows, that will work for you. So I've answered that one. Next one, do we need to configure anything to put both questions and associated answers in the same shard? So there's a couple of things here. So I index these with parent-child relationships. And when you index documents with a parent-child relationship, when I index the answers, I do have to say, hey, here is the ID of the question document that this answer relates to. And it is also a question document that you're looking for as well. So when I index answers into Elasticsearch and tell it that piece of information, Elasticsearch will go and index that answer on the same shard as the question to which it relates. So with parent-child relationships, the parents and the children do live on the same shards, and it has to be that way when you index the data. So you have no choice. You have to specify that if you use that kind of relationship. If you're not using parent-child relationships, you can also have documents to live on the same shard within a cluster. And that is using something called routing. So when you index a document, you can specify a routing key that says where that document should go and be indexed. You don't tell it specifically which shard that is. What happens is a hashing algorithm runs over that routing value that you give it, and the hash that's produced from that hashing algorithm is then used to determine which shard it lives on. But it's a consistent hashing algorithm. So if you want a collection of associated documents to live on the same shard, you can use the same routing value to have them be indexed on the same shard. This is often useful, for example, if you're running a site that's a global site, for example, and you want documents that are related to a particular geographical area to live in one shard in the same index, and documents related to another geographical area to live on another shard. You can use routing to do that. Alternatively, you might decide to index those into separate indices for different geolocations too, and then search across individual indices or multiple indices as and when you need to. Okay, the next question is, could you share some insight of Stack Overflow search volume as compared to redirect from Google? That's a good question. I don't have the figures to that, sadly, because that would require having inside knowledge into Stack Overflow, and I don't have that knowledge, unfortunately. I only have the data that's available to everyone to have a look at. So yes, we don't know how many how many searches happen on Stack Overflow as compared to Google. I suspect most of that traffic actually comes from Google or other search engines. Okay, so does Elasticsearch support defaulting creation date to indexing date and updating the last updated date whenever a document is updated? The answer to that is no. It's perhaps a little bit more nuanced. So if you index data using, excuse me, using Logstash or Filebeat, both of those will, I believe, if I remember correctly, append a timestamp at the point of time at which that document is indexed, which may be used as part of that indexing process and persisted as a field. But if you're indexing documents in any other way, then no, by default, there is no indexing date that is taken to be the creation date. You have to specify that yourself. Last updated date, whenever a document is updated, again, similarly, when you update a document, you would need to also specify that this is the date that I updated it, and you would have to send that through as a parameter. If you're persisting it on the document, you would have to send that through as a parameter when you're updating the document. So next question, if we use Elasticsearch as a database for Stack Overflow, can we create single index for both post and response question and answer? So yes, so that is what I did here, was to create an index which had a parent-child relationship in there between question and answers, and that post index that I created contains both the questions and the answers. You could, which if I'm reading between the lines on this question, potentially, I think it might be asking, could you index the answers as a collection on a question document? Yes, you could do that too. You could do that too, yeah. One thing to kind of think about if you are going to do that is if a question was to then get a new answer, and you wanted to add that answer to the collection of answers on a particular question document, what would end up happening is it would end up re-indexing the whole document there. But what you could do is you can handle that with a scripted update, similar to what I did to add the tags to answer documents. You could use that to add another answer to a question document and let Elasticsearch handle the updating of that document internally. So next question, can we plug in this dashboard to our custom apps? You have the ability to iframe dashboards in other apps. You can do that. Alternatively, if you were wanting to show visualizations, bespoke visualizations in your own applications, you might decide possibly to write your own visualizations using something like D3 and call the Elasticsearch APIs in order to fetch the data to do so. It just depends, I guess, really on how much customization you might need when you're displaying it within your own applications. Let me see. Okay, didn't get completely on how you read the data from Stack Overflow. So Stack Overflow provides that data as a collection of XML files that you can download. So I downloaded those files ahead of time. So I had them on disk, and then I had a small application that I wrote using the official .NET client that would then stream questions and answer records from those files, indexing them into Elasticsearch. So I wrote a small application. You might have used Filebeat or Logstash and pointed it at that XML file to do that streaming and indexing into Elasticsearch for you. But being an engineer working on the .NET client, it was very second nature for me to write a small application to do so. Okay, next one. Are we going to get these ES queries which were used? So I can make available, so I've made available the indexer. I can also make available the Cabana saved objects for, which would allow you then to take that file and import it. So if you've indexed the data into a cluster, Elasticsearch cluster yourself, and you then want to be able to visualize that stuff and see all of those visualizations that I've already created, I can export those and provide that file too, so you can import it into the same Elasticsearch version, and you will see all those visualizations. Yeah, I can do that. That's fine. How can we handle UK and US English words search in Elasticsearch, like color? Yes, synonyms is one way that you can handle that at index time. Another way that you can handle it at search time is potentially using fuzzy search. So using things like Levenshtein distance to perform fuzzy search across those. You might even take the additional step to potentially normalize that data beforehand, although there are many ways that you can analyze it to be able to change that data. So you could write an analysis chain that could go through and normalize words, US words to English words. That's something that's possible to do. Next one, are the machine learning and graph features only available in the cloud-hosted offerings of Elasticsearch? That's a very good question. So machine learning and graph, they are both features that are available within the gold and platinum license levels of Elasticsearch. So they are paid features. They are available within Elastic Cloud, depending on the level of Elastic Cloud subscription that you're using. So I'm not overly familiar with which parts are available at which level. Suffice to say, obviously, that the highest level has all the features available, but it would be worth looking at what is available there on Elastic Cloud. So Elastic Cloud does come with many of the paid features bundled as part of the cloud SaaS price. If you wanted to be running Elasticsearch self-managed, either as a cluster on VMs or using ECE, then you can obtain a license, a subscription for those gold or platinum features to be able to use those in your own environment. So next question, how to handle C++ and C# keywords in a search with standard analyzer as it is analyzed keyword into C? Yes, that's a very good question. So the answer to that is actually in that GitHub repository that where the indexer is that I have. So within there, I've configured a small analysis chain that sets up a character filter that will go through and essentially replace C++ with the actual words C++ and C# with C#. And it goes through and simply does a match on common programming languages in order to extrapolate them out to their word forms. Because as you quite rightly say here, the standard analyzer, the way that the standard analyzer ends up tokenizing text is to use something called the Unicode text segmentation algorithm, which would end up, as you say here, removing the plus symbols and the hash symbols from those keywords, which are important when you're trying to search on programming languages. So yes, analysis chains can sort that for you. Character filters is one way of doing that, and character filters run before the tokenizer, which splits text into tokens, happen. So you have an ability to manipulate those things before they end up being split into tokens and then further filtered. That's a good question. Can we integrate these visualizations in a customized web app? I believe I've answered that one. The answer is yes, you can embed them with iframes, or you can write your own bespoke visualizations and query the Elasticsearch APIs yourselves, and you can do many more things that way. Yeah, you can go completely custom that way. Can you just explain to us how you're relating posts, answers, and users in visualization? Yes, okay, so I only have the two indexes that we were looking at here, the posts index and the users index. So the relationship between those two indices, or documents within those two indices, there is no relationship within Elasticsearch between those documents. You could potentially query on posts, for example, and get the user IDs out and use those then to query the users index. Or what you might decide to do if you need data about the users in questions or answers, you might decide to denormalize that data at the point of indexing it in order to surface that data over to when you're looking at questions or answers. So is Elasticsearch a good use case for aggregation heavy operations involving nested documents? So nested documents are one particular way that you can index a collection of documents on another document. Nested, you know, they have many benefits whereby you can, obviously you can query on those things at the same time. they do come with a slight performance penalty in terms of the way in which those things are internally persisted within Elasticsearch. It really depends on the use case, honestly. Without knowing any specifics about the use case, it's kind of hard to answer that. I would say if you are performing for extremely heavy aggregations on very large data sets and lots of concurrent aggregations in that way, you may consider denormalizing out of nested documents potentially, and denormalizing those nested documents into a collection of individual documents and duplicating the parent or the root information onto each one of those documents. But it really does depend on the actual use case to know what the right answer is there. I would honestly suggest also maybe perhaps prototyping a couple of ways to figure out which one is going to work best. Okay. Is it recommended to use Elk as a database for a small web app and remove the dependency on using MongoDB or any other database? Well, again, it really does depend. There are many customers that use Elasticsearch as their primary data store. There are many customers that use it purely to power their search or purely to power their analytics and aggregations. So yeah, there's no right answer there. It probably depends on what you're doing with MongoDB in terms of whether Elastic could be used as a suitable replacement. Obviously, you have the advantage of having the ability to full text search over all of your documents and over multiple indices very easily in Elasticsearch. And you have the ability to update and perform CRUD operations on individual documents. So the answer there is it does depend, but potentially, yes. Okay, so in a relational database management system, we use, so large objects, binary large objects. What data types to be used in Elasticsearch? Can they be stored in the inverted indices? So that's a good question. Blobs typically large binary objects. So there is a binary data type within Elasticsearch, so you can index binary data. But if I would say it's probably like a large ones, probably not a great use case to actually persist within Elasticsearch. So i.e. using it to retrieve those on the source document. You might decide to store those in probably on the file system, because or on a file system, maybe a distributed file system in some way, because what you're going to do is that when you return documents to a particular search and you're also asking for the source documents, those binary large objects are going to be passing across the wire every single time, which may not be may not be very efficient or performant for your application. What you might decide to do potentially there, and what I've done previously prior to Elastic, is to index just the file paths, the share file paths to particular documents, so that they can be retrieved from the file system based on the results, search results that come back. And that worked very well. You obviously need some kind of reconciliation process to go through and ensure that those two things are kept in sync. But that we had a lot of success with that previously. So throw some light on use cases for nested documents versus parent-child relationships. Again, they kind of serve slightly different purposes. Yeah, they serve slightly different purposes. One advantage of nested documents is that you have all of the data there on one document. So performing nested queries or nested aggregations on those nested collections is fairly straightforward. Similarly, you can do that with parent-child relationships. One advantage of parent-child relationships is that you can add a child document independently of the parent document. So with nested data types, you effectively end up having to update or reindex the entire document, including all of the nested sub documents when you update that. Whereas with parent child, you can add a new child document for a parent without needing to update any of the other ones, any of the other documents. How can we show more questions with more answers as top results? So yes, that's, there's a few ways that we could do that. We could say, we could put an ordering on the search to say, yeah, order by, you know, questions that have a higher answer count. That's kind of one way to do it. So by default, they come back as in the highest scored way. But if you want to search and be able to show those questions that have the highest answers to them, then you might consider using something like a function score query. So a function score query allows you to perform like a full text search query or any other kind of query, but also then apply a set of functions to documents that are a match for that query. So those functions then allow you to take particular attributes of the matching documents and use those attributes to influence the score for that particular document. So one of the things you might decide to do here is run a function score query that does a match and has your full text search query in there, and then have a function which uses the field factor function to then look at the answer count field. And if the answer count field, you use that score there or that count there to basically influence the final score. So say, take that and multiply the score for the full text with that answer count to get the final relevancy score for that document. So that's how you can surface questions with a higher answer count higher. So let me see, a few more questions to go. What are the best practices to update stop words after data is indexed? So once data is indexed, you would need to reindex that data in order to, you would need to reindex those documents in order to update those stop words. So you can update the stop words list, but that won't, sadly, that won't affect any already indexed documents. You would need to reindex those in order for the new stop words to be applied. So if you've indexed those documents and kept the original source JSON that you sent in when you indexed it, which by default you will have done within Elasticsearch, you would be able to update the stop words list or dictionary or however you've configured it. You would then be able to run an update by query across the existing documents in order for that new analysis to be applied to them. So it might be the case that that stop words field might be set up on a new field potentially within the mapping. But yes, you can run an update by query to have existing documents be updated with a new mapping. You can't change, so I should caveat that by saying there are certain properties or certain fields that you can't change by reindexing. Like you can't change, for example, a field type from one thing to another. You can't change it, say, from being like a date field now to being a numeric field. You wouldn't be able to do that without reindexing the document into another index. So that's something to be aware of. If there's an iframe, there's a security constraint. Yes, potentially. You can configure cores, so cross-origin resource sharing on Cabana to allow you to do that. To say that this particular site is allowed to embed iframes from there, and no others are. Again, though, equally, you might decide to write your own visualizations and query Elasticsearch directly. Please provide the mapping JSON that you used. So it does exist in the GitHub repository, but it exists in C# code. So you would be able to run that C# code against Elasticsearch and see what the mapping is for it. But it does exist in that repository. I'll double check to make sure it is there. But yeah, it is there, and it should be there in C# code. Can you use ES to replace Spark? Good question. If not, why? Thanks. So they kind of serve slightly different purposes, I think. There are newer APIs within Elasticsearch that perform similar actions to what you might decide to do with batch processing with Spark. So for those that are not familiar, in Elasticsearch 7.3, I believe it was, we introduced a set of APIs called the data frames APIs. And what those allow you to do is, whilst you're indexing data or already indexed data, you can take that data and pivot it and transform it in many different ways, or like extract, build like entity-centric indices out of log event data, for example. And you can do that with the data frames APIs, which is similar to what a lot of people end up using Spark to do. So there are some ways that, yes, you can perform similar functionality to what Spark does with the data frames APIs. Yeah, so I would recommend going and checking those out and having a look at those. I believe they will be going GA very soon. Where can I find the internals of Elasticsearch v7? So the internals of Elasticsearch, the source code for it, so that's available on GitHub. So both the open source code and the commercial, the paid code for Elasticsearch is available on GitHub, and github.com/elastic/Elasticsearch. So questions there about where do we find the programming language character filter code in C#. It should be there within the create posts index mapping part there. So yeah, you should be able to find it there. I'll double check, make sure it is there, but you should see it there. Okay, that is all of the questions. So I think that probably about wraps it up. If you do have any further questions, or you have some feedback or additional comments, as I noted on the slides, you can find me on Twitter at forloop, FORLOOP. Yes, thank you very much for attending.